Here we're going to analyze the relation between the pair density and the electronic correlation. As it involves the position of two electrons, the pair density is going to be quite directly related to the electronic correlation. So remember that the pair density, the definition of the pair density is the following. A joint probability of finding an electron of spin sigma at point R and another electron of spin sigma prime at point R prime. Okay, in order to relate that with the electronic correlation, we are going to rewrite the pair density in the following way. Okay, we can see that the pair density could be considered as first, the probability of finding an electron of spin sigma at point R, and this is quite straightforward, this is just the spin density, times the conditional probability of finding the second electron of spin sigma prime at position R prime once we have found an electron of sigma spin state at point R. And we are going to call that conditional probability N2. It's going to depend on R prime, sigma, and sigma prime. And of course, we don't know what's going to be the expression of this N2. And this N2 is going to, that's the one, the function that will contain all the correlation between the electrons. Okay, and for example, if we consider that the electrons are independent, so that if finding the second electron is independent of the first event of finding the first electron, so we are in this independent electron approximation, then what we might expect is that this conditional probability, this N2 function, will be just the spin density, the probability of finding an electron at R prime and sigma prime. Okay. Then in this case, within that approximation, we might expect that the pair density will be just the product of these two spin densities. However, this is not exactly that, because this pair density, it satisfies some rules that we have to consider. For example, this is one of the some rules that the pair density satisfies. That's the following. It's very interesting to check. You should check it. That's the integration over the R prime and the summation over sigma prime of the pair density is just n minus 1. Just remember, n is the number of electrons times spin density of sigma spin state at point R. Okay, that's one of the sum rules. And if we just apply here the definition we have considered for the new way of writing the pair density, which is the product of n times the conditional probability times n2, then we have the condition that this conditional or the constraint that the conditional probability n2 needs to satisfy. This one. Okay, the summation over sigma prime, the integration over R prime of the conditional probability of this N2 is equal to n minus 1. And if we, as we have considered here, in this independent approximation, we have considered that the conditional probability is just the spin density. We plug here the spin density, the condition that, considering that the conditional probability can be written in this way, then in this case we'll have that the integration over the spin density and the summation over sigma prime is given equal to n and not n minus 1, and this is the condition that has to satisfy. So therefore, within the independent electron approximation, the conditional probability cannot be just the spin density. It's close to that, we might expect something close to that, but it's not, it cannot be exactly the spin density. Okay, so, but following that idea, in order to have or define another function that will incorporate this correlation, so we are going to rewrite the pair density in the following way. the density, as we did before, times, okay, that will be the conditional conditional probability n2, and the way that we are going to write n2 is the following way: n, the spin density at r prime sigma prime, in a similar way as our first guess for an independent electron approximation, plus what we're going to consider, where we're going to call the exchange and correlation Hall density. And it's going to be a function, of course, that we don't know which is the exact expression for this function. It will depend on the system that we have. It will depend on r and sigma and r prime and sigma prime. And we'll see later why we are calling that Hall, okay? Because there are several rules, some rules, as the one that, for example, here the per density has to satisfy, that the exchange and correlation Hall here is going to satisfy, of course. And this exchange and correlation Hall, as the name says, staying, it's going to give information of this exchange and correlation, because in the independent electron approximation, we might expect that the pair density is going to be very close to the product of these two functions. So everything that goes beyond that independent electron approximation is going to be included in this exchange and correlation Hall. Okay. And why we are calling that Hall? Because this exchange and correlation Hall satisfies two interesting rules or constraints, right? First, the Hall is usually, although it cannot be always like that, it's going to be negative and integrates to -1. That's very easy to check that the integration of that contribution over r prime, the summation over sigma prime, it's given -1. That's the reason of a Hall. The integration over the whole this function is given -1. And actually, even though it's not always, it's negative. And second, it will be interesting to check that. You should check this. It's very straightforward considering just this sum rule. It's very straightforward. Okay, and the second constraint is the following. Since the pair density cannot be negative, and just following the definition we have considered for this exchange and correlation Hall, but the product of these two functions cannot be negative, it should be positive. This is positive, of course, by definition. This is so we have that this one should be positive as well. But we know this is positive, but this is usually negative. So the following constraint has to satisfy in order to the sum of these two terms are positive. So this constraint has satisfied. We know that this is usually negative, but the exchange and correlation Hall should be greater or equal to minus the spin density at r prime with the spin state sigma prime. So these are the two constraints that we have to take into account when dealing with the exchange and correlation Hall. Again, that exchange and correlation Hall is the one incorporating that information related to the correlation between the electrons.